Hello and welcome to the Room of Lives. I'm your host, Neil. Today's episode is a recording of a conversation I had with my friend Stefan Eccles, a physics PhD student in the field of cosmology, who has been on this podcast before. I think we were driving to New Orleans for a trip when Stefan brought up Sabine Hossenfelder, who is a physicist studying quantum gravity. Sabine is author of a prominent blog where she has made a bit of a splash by being very critical of physicists wanting to spend a lot of money for large-scale experiments such as the Large Hadron Collider, because she thinks that those experiments are not well motivated. In this conversation, Stefan discusses this criticism with me, and we go off on a few tangents discussing physics. Since we were thundering down the highway, there was a wall of background noise which I removed, which results in our voices sounding kind of tinny, but it's at least understandable. If you enjoy visiting the Room of Lives, consider donating Ether, DAI, or other Ethereum-based coins to abronil.eth. That's abhranil.eth. Okay, so could you back up a little bit and this woman, what's her name?
So Josiah was telling me the other day about some recent arguments that Sabine Hossenfelder has made on her blogs.
Yeah.
And apparently she's written a book.
Okay.
But
and Sabine Hossenfelder is a theoretical physicist
Right.
and has some kind of a popular blog.
Yes.
Okay.
Yeah. And she's sort of now famous for being a stickler about things.
Yeah.
You might say a stick in the mud.
Yeah.
But she specifically thinks that a lot of the proposed next rounds of experimental physics are not well motivated.
Yeah.
So, the example from recent past is the Large Hadron Collider, this enormous investment,
Yeah.
an enormous international collaboration,
Yeah.
was mostly motivated to discover a couple things. One was the Higgs,
Yeah.
which had firm theoretical grounding. People really believed it was going to be there.
Yeah.
They were quite confident. So its discovery was a major achievement, or its detection was a major achievement, but
Yeah.
it was not a surprise.
Okay.
And then the other thing that some people would have said was also on firm theoretical grounding was supersymmetry. That this type of symmetry should be utilized in nature, and if it is, there's a bunch of different ways to do it, but one of the most simple, the minimal.
Wait, could you tell me a little bit about what is supersymmetry?
It's a major tangent from where I was.
Okay. Let's yeah.
Yeah, so it's just a theory in particle physics that said
Yeah.
all the standard particles, the
Yeah.
particles in the standard model of physics,
Yeah.
should have a supersymmetric partner, which would every boson would have a fermion partner,
Yeah.
and vice versa.
Yeah.
And what the masses of these extra particles should be is a big question. It depends on how exactly you. It's not exactly specified by supersymmetry alone, but one of the simplest models said, "Oh, the masses of the supersymmetric particles should be right in the accessible range of energies that we can reach with the Large Hadron Collider."
Okay.
So it was also expected that when we turned on the Large Hadron Collider at these energies,
Yeah.
there should just be a bunch of new particles showing up.
Yeah.
That was,
Did you hear that?
yeah, that was like a rock.
Okay. Oh my god. So was the energy required to investigate these supersymmetric particles a larger or a higher energy than that required for the discovery of the Higgs boson?
Maybe the prediction for what the masses of the supersymmetric particles should be is not that precise, but I think they're very comparable.
Yeah.
That's the idea. It was we don't know precisely the mass of the Higgs, but it should be in this range, therefore we should be able to detect it.
Yeah.
And then likewise with the supersymmetric particles, the lightest of them at least should be in a range that's detectable by this detector.
I see.
If you use the minimal supersymmetric or minimal I forget what it's called, the MSSM.
See, the reason that I'm asking is how much extra resources was required to explore these supersymmetric particles versus what you already had in place for discovering the Higgs boson?
It's a good question. I don't know. I think they're very comparable. So that if you built, I guess when the collider was designed, it was with both things in mind, and I think they were supposed to fall roughly in the same energy ranges. Like, we built it with definitely with in mind that we were going to detect the Higgs, and that you wanted to have like a comfortable margin that you could access that would give you clean access to the Higgs, and then and it should also cover the easiest supersymmetric particles. But I don't know whether one was really setting the lower bound that you needed to be achieved. But in any case, those were the two of the main motivations for building the Large Hadron Collider at the scales that we built it. And so this Hossenfelder person has argued recently that all of the arguments that were telling us why we should expect the supersymmetric particles to show up at that scale were all bullshit, and no one should have expected anything. Like no one should have expected that they're at that mass versus hundreds of TeVs or some just crazy large mass or whatever. There's no reason to expect it to be one thing or the other. And so what she's rejecting is a type of argument that particle physicists use called arguments based on naturalness. And naturalness has to do with the idea that if you have a model for some system with several dimensional parameters in it, then the only natural numbers that you can get out of those models are the only numbers that should be
like dimensionless numbers.
Dimensionless numbers. Well, also dimensional numbers, but dimensionless numbers should be like simple ratios of or simple combinations of the parameters that go into the model. So, like, one example is I was telling you about this spin chain stuff that I'm doing. We've got a Hamiltonian, and we observe some weird oscillatory behavior in how the entanglement. It kind of reaches its saturated value, but then it dips down and goes back up and down and back up. And it seems to oscillate. And there seem to be two frequencies that are dominating the oscillations. And so naturalness, or like it's physically sensible to say, well, probably what's setting those frequencies is a combination of the energy scales that go into the Hamiltonian. So there's only a few dimensional numbers in the model. And so you won't get some random frequency to show up in the behavior of this system that's completely unassociated with those energy scales. That will be like determined by those energy scales in some combination. So it's kind of a similar argument that
but when you say natural numbers, I'm getting confused with the mathematics of natural numbers are just like 0, 1, 2, 3, 4, 5, the whole numbers, right?
It's unassociated with that definition.
Okay.
It's just that your model has certain dimensional parameters. The types of behaviors you see should be governed by those dimensional parameters that are in the model, and you shouldn't get behaviors that occurs at scales that are completely unassociated with those. It would take some really weird model to intentionally use those dimensional parameters in some math formulas and end up with behaviors that occurred at some characteristic scale that was very different, or that wasn't at least related to a simple combination or ratio of those. So in naturalness, in particle physics, it's usually just the way that you set up the Lagrangian. You put a coupling in front of each of the terms, and if the dimensions of the fields themselves are set up to all be comparable, then the coupling should be basically order 1 numbers. They should be like, should be between, or they should be not too different from 1. They shouldn't be at a strength of 1 billion, or they shouldn't be at a strength of 0.00000001. It should be, if you've defined the dimensions of the fields to be comparable, they should talk to each other with a dimension or an order 1 parameter.
Yeah.
And if you have something where that coupling is suppressed, so that your coupling constant between these fields is actually 0.00000, or like 10 to the minus 20 or something.
Yeah.
That doesn't just happen naturally. Okay. That's like something in the system, something in the physics is leading to that
malicious
suppression. God. Yeah, exactly. There's something physically suppressing that coupling. Yeah. And often in physics, what that means is you have a symmetry which ordinarily would forbid it, and then that symmetry is is like barely violated by some messy processes. But there's a symmetry that's like it basically sets the base value of that at 0, and then you can get some quantum corrections or some like slightly broken symmetries lead it to deviate from that slightly. So like if you end up with a coupling constant that's really small, that usually means there's some extra physics that's like pushing that towards 0. Because ordinarily the natural thing you expect is for order 1 numbers to be the coupling parameters. Yeah. So naturalness is an idea that the scales that show up in your Lagrangian should all be order 1 numbers if you set them up comparably.
It doesn't sound like a very rigorous principle, but just something kind of like, it's like, makes sense. It's a kind of broad, vague principle that you can...
Right. And it's worked in some cases in the past. Like, people have noticed, like, this coupling is really small compared to all the other ones. Why is that? It's because this extra thing is going on. So it's like, it's given some guidance in the past. Yeah. But now it's kind of used all over the place. It's like, until we have reason to suspect that it's something other, we should just assume that the coupling is order 1. Order 1 number. It could be a little larger than 1, a little smaller, but it shouldn't be like many orders of magnitude different. Yeah. And so her main argument, that sort of reasoning is one thing that lets you make guesstimates for what these particle mass scales should show up at. And that's what kind of the type of thing that was used to, well, actually it's slightly different from that, but arguments based on naturalness of where the scales should be, barring some extreme thing that's pushing them to vastly different values, are what were necessary to make these predictions as to what the masses of the supersymmetric particles should be. Hossenfelder is like extremely critical of that type of argument. She says naturalness is BS. You should never, if we happen to have 5 coupling constants that are order 1, and then one that is like exactly 5 times 10 to the negative 300. Yeah. And it's like, it can't be 0, but it has to be precisely 5 times 10 to the... That weirdness, that it's like set to something so close to 0, but not quite, physicists would start referring to that as fine-tuned. Or if, like, in order to match predictions, if you had to have a constant that fell at just a particular scale related to the other constants, where you need some amazing precision, like you have to go out to like 100 decimal points and get it accurately tuned to this value relative to the other coupling constants, or else something would fall apart. Yeah. And yet there's no mechanism known that puts them at those values relative to each other. They just happen to fall precisely at these values. That's what goes by fine-tuning. Yeah. So naturalness... evidence for God. I've heard arguments. Yeah. Yeah, that's definitely... Yeah, that does come up in discussions about God. So, like, if there's not a known mechanism to set these constants at particular values, and yet they have to be something that's vastly different from just order 1 parameters, as if they were just drawn from a flat distribution around 1. Yeah. Some Gaussian, drawn from some distribution. She's saying there's no reason at all to expect that they're drawn from any particular distribution. It could well be that we just live in a universe that looks incredibly fine-tuned, and that we have some constants that are vastly different from others, but for no physical reason other than that's what they are. Okay. So she rejects arguments based on naturalness, which is one of the main tools that physicists use to guess at what the natural scale should be for any given new particle. Yeah. So Josiah was telling me that she's she's like, as he said it, she's against everything. She's against the big new experiments. She says they're not well motivated. She's even against doing small tabletop experiments because she thinks they're not well motivated. So we were discussing, like, what does she think is well motivated? And she has like
wait. I thought she might be against, because I don't see why you shouldn't do experiments anyway, except for the fact that they cost money. So I imagine that she might think that let's not do big LHC scale experiments. Instead, let's redistribute the funds to many other smaller experiments or whatever. But if she is against all experimentation, why is... I don't understand. Why does she want...
I agree. I think, like, I had heard about her views before, and I thought it was exactly that.
Yeah.
Like, she doesn't want to fund these massive collaborations for colliders.
Yeah.
She just wants to do smaller, one-off experiments that explore different corners of theory.
Yeah.
Until there's something really new to go off of.
Yeah.
But he was telling me that she also thinks those experiments are not well motivated at this point. It's like, standard model of physics makes great predictions everywhere except for potentially at extremely high, like, there's known problems with it. And until you can make a real theoretical breakthrough,
okay, so maybe her, like, just general principle is to do only really well motivated experiments where you're, like, very sure of what. So she herself, is she an experimentalist or a theoretician?
No, she's a theorist.
Yeah, that makes sense.
Yeah, but she also thinks half of the theory that people are doing these days is BS. So she's, like, critical of so much.
I see. Okay.
Because if the theory uses arguments like naturalness,
yeah,
she thinks it's out the window.
Okay. I mean, I guess it helps in a scientific community to have all kinds of voices like that.
Yeah.
Sometimes. Okay.
So, apparently, I mean, I was asking, like, I'm all giving you the second hand. I haven't even read her blog posts about this.
Yeah.
But, Josiah was telling me the few realms of modern physics that she thinks are really worth investing in is, like, LIGO type stuff, gravitational wave type stuff.
Yeah.
And foundations of quantum mechanics stuff, which seems kind of random to me, but...
Experiments for that?
Yeah. Yeah, in order for there to be experimentally testable differences in your theory about foundations of quantum mechanics, you have to break from the mainstream, kind of.
Okay.
Like, there's some versions that say quantum mechanics is incomplete. Like, one of the main things that's unexplained, or that the standard theory leaves in a place that's very unsatisfactory, is there's this notion of wave function collapse.
Yeah.
And every measurement causes a wave function collapse.
Yeah.
Like, what's actually happening there? Is it really this discontinuous thing where you can have a wave function that's defined throughout the universe, and then someone here makes a measurement and suddenly it collapses to, like, the particles here now?
Yeah.
Like, that seems very unphysical.
Oh, can I tell you a little anecdote here? So, when I was in India and I was getting my master's thesis advisor was in the field of nonlinear dynamics. And one of his original contributions to the field was a particular kind of, a particular kind of bifurcation. A bifurcation is when you're tuning a certain parameter in some kind of a usually nonlinear system, and it suddenly makes a kind of discontinuous and abrupt transition in its behavior from one kind of behavior to another kind of behavior. Suppose that could sometimes be that in one regime of the parameter, it has an equilibrium, a single equilibrium point.
Okay.
In its state space. It's got a single equilibrium state. But as you tweak that parameter, that equilibrium point maybe first, like, shifts gradually. That's a continuous change, no problem. But at a certain parameter value, it suddenly becomes an oscillation between two equilibrium states. So the system splits from having one steady state to having two steady states that it keeps flipping back and forth. And that's an example of a bifurcation.
Okay. Nice.
So this professor his main contribution was finding out a new kind of bifurcation in nonlinear systems, which had to do with systems that had two regimes of dynamics. So we're talking about two different things here. One is a bifurcation where it goes from one kind of behavior to another kind of behavior. But he was looking at this for systems that already had like two regimes of behavior. So it was some kind of system that went through like maybe a cycle or something where in one regime it has certain dynamics, in a different regime it has a different dynamics, all within the same cycle. That's like one regime of behavior for the system, and it has two behaviors, behavior 1 and behavior 2 within that single behavior, and he was looking at bifurcations of that kind.
Nice.
And so when I was in my final year, I did my master's thesis with this person, and he said, I have a couple of ideas for things you could do your master's thesis on. And one could be, he thought of the wave function collapse as being a kind of discontinuous, like a dynamical regime change like that. And he was like, can we do this nonlinear bifurcation theory on the quantum mechanics of wave function collapse? I mean, that would be a major... He was always interested when two apparently unrelated fields of physics or fields of knowledge gets connected together. And he was like, can we do some nonlinear dynamics bifurcation theory on this sudden state change that happens in quantum systems when you do observations and it collapses wave function. And I thought it was such a big thing for me to bite off that I was like, oh no,
that does sound intimidating.
Yeah, I was like, I can't do this as a master's thesis.
But that's like considered one of the main possibilities. If you don't buy the Copenhagen interpretation, which isn't really a full interpretation, it just says, let's not bother with what wave function collapse is, let's just use the rule for wave function evolution up until a measurement, and then let's just say it collapses.
Yeah.
But like, Penrose, for instance, also believes in something like that. Like, there's a dynamical collapse phenomenon that occurs really rapidly and probably involves really nonlinear physics. I don't know how the bifurcation relates exactly, but...
Yeah.
But yeah, that's like one of the main alternatives to the Copenhagen interpretation, is that it's actually a physical collapse process that's occurring, and we just don't know the equations that govern that collapse.
Yeah.
Or we don't know what sets it up. I think Penrose's personal theory has mostly been ruled out by now, because it postulates like... It actually postulates that it's related to gravity. It's like when the size of the system reaches a scale where gravitational effects become large, then that triggers a wave function collapse or something.
Yeah. So back to what you were saying about Hossenfelder, saying that one of the fruitful directions to do experiments is foundations of quantum mechanics and wave function collapse.
Right, and I don't know quite what the reasoning is, but I assume it's related to testing ideas about quantum gravity. She thinks we'll actually make progress if we first clarify the way we've set up quantum mechanics and what's actually happening with measurement and stuff.
Yeah. Then
how quantum gravity works should be clearer, because one of the big mysteries in quantum gravity is like, well, even defining sensible observables is kind of hard in GR.
Yeah.
But like, okay, so yeah, one situation that you could imagine testing, which I was discussing with Josiah last night, was like, you create a single particle in a superposition of states where it's localized here and here.
Yeah.
And you get it, and you have, it's a massive enough particle that you should be sensitive to the gravitational effects of both. So like, a superposition of metrics is a really weird thing to think about.
Yeah.
It's like the space, you have a superposition between this ordinary flat space and one that has a bump in it.
Yeah.
It's like, that's different from ordinary, even...
Isn't that just this is going to be such a stupid... Just the sum, the resulting metric is just going to be the sum of the two metrics? No?
That's what it means to be in superposition, yeah.
Okay.
But like, what does that mean physically? Like, which one do we experience?
Don't you experience... Okay, once again, stupid. Suppose that you were just floating in outer space, and Jupiter pops up to your left, and it creates a certain metric where you're standing, and then Saturn pops up to the right. The thing that you experience is the combination of their gravitations, right?
Yeah. Yeah, so there's the okay, so... really, GR is very nonlinear, so you can't just superimpose solutions.
Okay.
But in like a linear regime, yeah, you'd say we just feel the effects of both fields.
Yeah.
But I think this is slightly different in that, like, it's a superposition between the possibility of feeling Jupiter over here
Yeah.
and not over here versus feeling it here and not over here.
Yeah.
So yeah, I don't know what that looks like really.
Yeah.
I don't know what it means. If you're in a mixture of space times,
Yeah.
or even if you created like an interference effect between two space times, I don't know. It's just weird to think about.
Yeah.
It might have a simple answer though, if it's not some really highly nonlinear thing.
Yeah.
I should probably be paying attention to directions now.
Thanks for joining us today in the Room of Lives. See you next time.